welcome to the deep dive. So you flagged some really incredible recent JWST findings about the exoplanet K2-18b.
That's right. It's generating a lot of buzz.
Yeah, I mean, it's in the habitable zone, but the really kind of mind-bending idea is this Haitian possibility, a water ocean under hydrogen.
Exactly. That's the hypothesis getting a lot of attention.
So what we want to do today is cut through the complexity and really pull out the key insights about K2-18b's potential for life from these new observations.
Yeah, let's dive into what JWST actually saw and, what it might mean for that big question, are we alone?
Okay, let's start basic. Paint us a picture. Where is this place?
So K2-18b orbits a red dwarf star, K2-18. It's in the constellation Leo.
And how far?
About 110 to 124 light years away. So not exactly next door, but cosmically speaking.
Relatively close for these kinds of studies, yeah. And this star, K2-18, it's a red dwarf.
Right. Smaller, cooler than our sun, moderately active, which is interesting. And there's actually another planet, K2-18c, but B is the one we're focused on.
Gotcha. And how did we even spot K2-18b in the first place? That was back in 2015, wasn't it?
Yep, 2015. It was the Kepler Space Telescope during its K2 mission. They used the transit method.
Ah, right. Watching for the little dip in starlight as the planet crosses in front.
Exactly that. Tiny, tiny dips. Kepler was amazing at spotting those.
So what did that tell us about its, size and weight?
Well, we know it's pretty hefty, about 8.6 times the mass of Earth, and radius-wise, it's around 2.6 times Earth's.
Okay, so quite a bit bigger. What does that density suggest? It sounds sort of in between.
It is. That's the tricky part. It's not dense enough to be purely rocky like Earth, but not light enough to be a gas giant like Neptune. It's in that sub-Neptune or mini-Neptune category.
Which makes the atmosphere super important to understand.
Absolutely crucial. And the surface gravity, it's actually estimated to be pretty similar to ours, maybe around 1.18 times Earth's.
Interesting. Okay, so bigger, similar gravity, and the big one. Where does it sit relative to its star?
Right, smack in the middle of the habitable zone. Yeah, it gets roughly the same amount of energy from its star as Earth gets from the sun. Its orbital period, its year, is super short, though, about 33 Earth days.
Wow, a fast year. And its temperature. I saw something like -8 Celsius.
That's the equilibrium temperature, yeah. Basically what its temp would be without an atmosphere soaking up heat. But if it has that thick hydrogen atmosphere,
Then things could be very different. Which brings us back to this Hyson idea. Can you remind us what that means again?
Sure. Hyson is short for, well, a hypothetical type of planet with a hydrogen atmosphere, the Hya, covering a global water ocean.
Hydrogen atmosphere, water ocean.
Got it.
Right.
Okay, so JWST pointed its fancy instruments at this world. How does it study an atmosphere from so far away?
It uses a technique called transmission spectroscopy. Think of starlight passing through the edge of the planet's atmosphere when it transits in front of the star.
Okay.
Molecules in that atmosphere absorb specific wavelengths, specific colors of light. So JWST catches the light that makes it through and sees what colors are missing or dimmed, like a chemical fingerprint left in the starlight.
Exactly. And its instruments, NIRS and NRSpec, are incredibly good at reading those fingerprints in the near-infrared light.
So what fingerprints did JWST find in K2-18b's atmosphere?
This is where it gets exciting. Clear detections of methane, CH4, and carbon dioxide, CO2.
Okay, methane and CO2.
And importantly, these are the first carbon-bearing molecules definitively detected in the atmosphere of an exoplanet in its star's habitable zone.
Wow. Okay, that feels significant. The building blocks for life as we know it. What kind of amounts are we talking?
The estimates are around 1% abundance for each, roughly. So, not just trace amounts.
Interesting. Anything else pop up in the data?
Yes, and this is the one causing the most stir. A tentative detection of dimethyl sulfide, DMS.
DMS, tentative. Why is that one so exciting, even tentatively?
Because here on Earth, DMS is overwhelmingly produced by life, particularly marine phytoplankton. There are very few known ways to make it abiotically without life.
Whoa. Okay. Tentative, but still.
Wow.
Any other detections or non-detections?
Well, interestingly, ammonia NH3 seems to be scarce. It was below the detection limits, which are pretty low, maybe less than 100 parts per million. And water vapor also seems maybe lower than some earlier Hubble results suggested, possibly because it's trapped deeper down, or we're just seeing a drier upper layer. Carbon monoxide also wasn't really seen.
Okay, hold on. Lots of methane and CO2, but very little ammonia. Doesn't ammonia usually hang out with hydrogen?
That's the key insight. In a hydrogen-rich atmosphere like this one should be, chemically, you'd expect ammonia to form readily.
So where is it?
One compelling idea, and this links back to the Hycean hypothesis, is that the ammonia is being produced, but it's dissolving into a vast water ocean below the atmosphere we're probing.
So the lack of ammonia actually supports the ocean idea.
It's consistent with it, yes. It's one of the main pieces of evidence favoring the Hycean model right now.
Let's go back to the DMS for a second. You stressed tentative, but if it is there, why is it such a potential bombshell?
Like I said, on Earth, it's almost exclusively biological. It's considered a potential biosignature.
But there's a catch, right? Something about the amount.
A big catch. The potential concentration needed to explain the tentative signal on K2-18b could be, like, thousands of times higher than the average DMS levels in Earth's atmosphere.
Thousands. Okay, that sounds extreme. What could that mean?
It means either you'd need some kind of hyperproductive alien biology churning out way more DMS than Earth life does, or there's some unknown, very efficient non-biological process making DMS in that specific environment something that doesn't happen on Earth.
And crucially, have we found DMS elsewhere in space without life?
Yes, actually. It's been detected in interstellar gas clouds and even in comets. And lab experiments show it can be formed through photochemical reactions, light interacting with other chemicals.
So finding DMS, even if confirmed, isn't automatic proof of life.
Absolutely not. It's a fascinating hint, a maybe, but we have to rule out abiotic pathways first, especially given the potentially huge amounts involved.
Okay, so connecting it all. The methane CO2 presence, the ammonia absence, and the tentative DMS all sort of point towards, or are at least consistent with, this Hycean water world idea.
They are consistent, yes. Current models show that an atmosphere interacting with a water ocean can reproduce these observed chemical abundances, particularly the low ammonia.
But we haven't, seen the ocean directly, right? It's still an inference.
Correct. No direct detection. And there are challenges. Depending on pressure and temperature, the water could be in a weird supercritical state, not like a liquid ocean we'd imagine.
Right. And could other models explain the chemistry we're seeing?
Yes, alternative explanations exist. It could just be a gas-rich mini-Neptune with no surface ocean, but complex chemistry happening deep in its atmosphere. Or even, potentially, a world with a magma ocean influencing the atmosphere.
So the jury's still out on whether it's truly Hycean.
Definitely. The current data is exciting, suggestive, but probably not quite enough to definitively distinguish between these possibilities yet.
This is fascinating, though. K2-18b seems to be pushing us to think beyond just Earth twins, doesn't it?
Exactly. If Hycean worlds are real and potentially habitable, it really broadens the scope of where we might look for life. They might even be more common than Earth-like planets.
And potentially easier to study with those big, puffy hydrogen atmospheres.
That's the idea, yeah. Hydrogen makes the atmosphere extended, easier for techniques like transmission spectroscopy to probe.
So what's next? How do we get closer to answering these questions about K2-18b?
The absolute top priority is trying to confirm or refute that DMS detection. That requires more observation time.
More JWST time.
Yes, more time is planned, specifically using the MURI instrument, which looks at mid-infrared light. DMS might have clearer features there, and it would help cross-check the near-infrared data we have.
And beyond DMS.
We need more detailed spectra overall. Better constraints on the atmospheric temperature structure, searching for other molecules, basically building a more complete picture.
And it's not just observing, right? There's lab work and modeling involved, too.
Oh, for sure. We need better theoretical models of Hycean atmospheres, magma ocean atmospheres, you name it, and lab experiments to simulate conditions and understand how these molecules actually behave and look in spectra. It all works together.
Okay, so let's sum this up. K2-18b, it's this intriguing world, habitable zone, hydrogen-rich atmosphere confirmed with methane and CO2, a first for that zone.
Right. Key finding.
Then there's this tantalizing but tentative hint of DMS, a potential biosignature, but huge questions remain about abiotic sources and concentration.
Needs confirmation, absolutely.
And this whole picture, especially the low ammonia, makes the Hycean world idea, water ocean under hydrogen, seem plausible, maybe even likely, but it's not proven. Other models could still fit.
That captures it well. It's a compelling candidate, maybe our best one for a Hycean world so far, but more work is definitely needed.
The ongoing research, especially with JWST, sounds like it could really unlock some secrets here.
We hope so. It's right at the frontier of exoplanet science.
Which leaves us, and you listening, with something to think about. As we find more diverse worlds like K2-18b, how might our actual definition of habitable need to change? Could life thrive in places radically different from Earth, places we haven't even properly imagined yet? And what new signs of life, what other biosignatures should we be searching for out there? Thanks for taking this deep dive with us.